Assalamualaikum ji. This is the final example, and this example will be encompassing each and every aspect that we have discussed so far. You have your circuit in front of you with a 50 volts DC source connected to a 20 kilo ohms resistance, then a 10 kilo ohms resistance and another 20 kilo ohms resistance. You need to find out the current through the vertically connected 20 kilo ohms resistance. A capacitor is connected at the right side of 0.1 microfarads. A switch is connected across the 10 kilo ohms resistance. Before the operation of switch, that is at time t less than 0, the 10 kilo ohms resistance is in the circuit, and when the switch operates at time t is equal to 0, or when it is in position for time t greater than 0, the 10 kilo ohms resistance gets short circuited and does not remain a part of the circuit, right? It says that you need to find the response for current through 20 kilo ohms resistance. Now, first let us find out V of t at t is equal to 0 minus, or t is equal to 0, or t is equal to 0 plus, or t less than 0 before the operation of the switch. V of t will definitely be equal to the voltage across the combination of 10 kilo ohms and 20 kilo ohms resistance, which are connected in vertical position. So using VDR, voltage division rule, simply we can have the value of V of t. V of t is equal to 20 plus 10 divided by 20 plus 10 plus 20 into 50, which gives us 30 volts, right? So now let us find out the value of V of t for t greater than 0, that is when the switch is operated and a long time has passed after the operation of switch. So I may write it all. In some textbooks it is stated at t greater than 0, and in some textbooks it is stated as t equal to infinity. Both mean the same. So at t greater than 0 or t is equal to infinity, V of t comes out to be 20 over 20 plus 20 into 50, which is equal to 25 volts, since the 10 kilo ohms resistance has been short circuited by the switch. The voltage across the vertically connected 20 kilo ohms resistance is simply the value of V of t at t greater than 0, which is 25 volts now. Recall the example in which we had two resistances and two capacitances, and we found the Thevenin equivalent resistance. Actually, in this example, in this numerical, we are combining the concepts that we have learned in previous examples. So let us find out the value of R Thevenin. Removing the capacitance from the points where the crosses are marked and replacing the voltage source with a short circuit, the two resistances come in parallel. The parallel equivalent of both resistances, since both are 20 kilo ohms resistances, the parallel equivalent is 10 kilo ohms. So now the time constant will simply be equal to R Thevenin times C. In the previous example it was R Thevenin times C equivalent. Since there is only one capacitance in this example, so it is simply R Thevenin times C, which comes out to be 1 milliseconds. So up till now, whatever it is written in red color, it is very simple, since everything has been performed in previous examples. I'm going to derive an expression for you. Recall the very first circuit in which we had a resistance and a capacitance which were connected to a source through a switch. I'm drawing the same circuit in blue color, and we perform the analysis on this circuit with zero initial conditions and with some valued initial condition. So recall the one in which we said that the capacitor was initially charged to some voltage V0. We had the solution for Vt equal to Vs plus V0 minus Vs exponential of minus t over tau. So what was Vs? Recall that at time t is equal to 1 time constant, we evaluated the value of voltage across the capacitor equivalent to 63%. And I told you to calculate the value of capacitance at 2 time constants, 3 time constants, 4 time constants, 5 time constants. So if you perform that, you must have seen that at 4 and 5 time constant, the capacitor is almost 100% charged. And if the value of time is increased beyond 4 or 5 time constants, the capacitor remains 100% charged. So we can say that Vs present in this equation is the value of voltage across the capacitor at some time t far greater than 0 or time t is equal to infinity, right? Or it may be termed as final value, right? So V of S can be called as the final value. V0 was the initial value. We defined it as the initial value of voltage across the capacitor. Again, Vs, we have Vs which can be written as V of t at t greater than 0, or the final value. So I'm going to generalize this equation. So the response or the value of V of t can be written as final value plus initial value minus final value times exponential of minus t over tau, right? So this is a general equation, and I will be using this equation to solve the circuit that is drawn at the top of this page. So V of t is equal to final value. What is the final value? Final value is 25 volts. The value of V of t at t greater than 0 or t is equal to infinity, or time t greater than 5 tau or 6 tau, 4 tau, 5 tau, right? So V of t is equal to 25 plus what is the initial value? The initial value is the value at time t is equal to 0 or t less than 0. That is equal to 30 volts. And again, final value which is 25. So we can have the expression for V of t, which is 25 plus 30 minus 25 exponential of minus t over tau. We have found the value of tau, which is equal to 1 milliseconds or 0.001 seconds. Simplifying this equation, we'll get 25 plus 5 exponential of minus t over 0.001. And in order to find the value of current, it is simply this voltage divided by 20 kilo ohms, since the 10 kilo ohm resistance is no more the part of circuit. So V of t divided by 20k is equal to 1.25 milliamperes plus 0.25 exponential of minus 1000 of t, right? So this example is basically encompassing the understanding of all the examples that we have done so far. Thank you very much. Assalamu alaikum.